All right, 6.2, definite integrals. Now, I don't remember if we did anything with these last year when I kind of introed it.
S little thing, we did a little bit. Just where we had to plug in the calculators.
Yeah, we'll be doing them by hand. So lovely. But to start out, we're doing, or looking at Riemann sums, which we have the summation from k equal to 1 to n. Okay, so that's what that's read as. It's the sum from k is equal to 1 to n of a sub k is equal to a sub 1 plus a sub 2 plus a sub 3 plus ... plus a sub n minus 1 plus a sub n. So it's basically all the terms from 1 to whatever n is are getting added up. Sometimes we will partition, which means to break up a graph into smaller subintervals, or, well, I should say smaller intervals that basically makes little subintervals. And so then the Riemann sum for f on the interval from a to b is s sub n is equal to the summation of k is equal to 1 to n of f of c sub k delta x sub k. And I promise that the problems that deal with this are not as complicated as this formula makes it look. It looks scary, but it's not. So we can do the definite integral as a limit of Riemann sums so this is the limit. Now it's like 2 bars, and I forget what they actually are called, but anyways, as the number in those, or as p, which is in those bars, goes to 0, the summation of k is equal to 1 to n of f of c sub k delta x sub k is equal to I. Where f is integrable on the interval a to b, and I is the definite integral of f over a to b. It's like differentiable, integrable.
Yeah, I didn't know it was.
Yeah, it's a weird word, and it's honestly kind of hard to say.
Yeah.
If I'm being like completely honest.
The more I say it, it sounds even less like a word.
Also, I'm looking, and I think this is just notation for partition. I was trying to remember what those lines meant because I don't use them very often.
Oh, okay.
Something about the norm of the partition, and that's how it's denoted. I don't know. It's weird. Okay, so anyways, we have an existence theorem, which tells us basically that a definite integral exists. That's what it means, that there is one. So this is the existence of definite integrals. I think definite integrals might be one of my favorite things in calculus. Like, cause like when you find, like, you're getting a definite value at the end.
Okay.
Like, you're plugging in numbers to get a single answer.
I like that. Okay.
So
This is promising.
that's why I tend to like it. When we get to indefinite integrals, which is just going to mean that you're not taking it, it's not going to be on an interval from like 0 to 50 or, something like that. When we get to those can be not as fun because there's not like an end result necessarily that you're trying to seek in terms of a number. So anyways, I don't know. I kind of think integrals are fun until you get all the special rules, then it gets a little stressful. But there's going to be more memorizing in this chapter, but I don't think it's in this section.
Did
So
you think last chapter was fun?
no.
Okay, cool.
I found
'Cause
last
didn't
chapter
either.
quite frustrating.
Because I didn't either.
No.
Because if you said yes, I'd be like, oh no.
No, chapter 5 is I think is the hardest chapter in the whole book.
Okay.
So you survived, you'll be fine. Can't say that Calc 2 won't be brutal when you get there. I hated Calc 2, but
Oh yeah, I heard.
Isn't that like multivariable calc? Isn't that what it is or whatever?
I think that's Calc 3. I enjoyed Calc 3. Calc 2 was awful.
I don't have to go that far. I don't know if I have to. I'll have to check.
I really, in level of like difficulty, it should be Calc 1, Calc 3, Calc 2. Like Calc 2 is the hardest in my opinion. Yeah. All right, all continuous functions are integrable. It's such a hard word to say. I also don't really know why I underlined continuous, other than I guess it's kind of like needs to be emphasized that if it's not continuous, it's not integrable.
I just did it.
Just because you did.
It didn't have to be. I don't really know why I did, but oh well. That is if a function f is continuous on the interval a to b. Now, notice it's on that interval. Okay, right? So a function might not be continuous everywhere, but if it is on the interval, then it's still okay. Then it's definite integral over a to b exists.
Are we gonna be able to get another test in before the quarter ends?
Well, yeah, wherever we're at, we'll take one.
Okay.
No, I'm not letting that be your only test. That would be, like, cruel. No, that would be cruel. It might be a small test, but there will be another test.
Okay.
I'm not letting that be 45% of your grade.
No, because that's actually insane.
No, yeah, I guess that would have been.
Some chapters it would have been okay. That one, absolutely not.
Okay, just making sure. Because I know it took us a while, so I was like, oh, I don't know.
This is a shorter chapter, I think.
Okay.
I want to say there's only 4 sections that we cover in this chapter. I don't remember if we have to cover this one section. 4 that we cover. So 6-2, 6-3, 6-4, 6-5, because I probably won't do 6-1. Because part of 6-1 is included in here, and this is the easier method.
Oh.
So that's why I just kind of... 6-1 is also word problems. And
Just get rid of that.
Yeah.
Kill that quarter.
It already reproduced from chapter 5, so don't let it reproduce again.
The definite integral of a continuous function. Can't spell. On the interval a to b. The subintervals delta x is equal to b minus a over n. Gives us the limit as n approaches infinity. Limits are coming back, in case you'd forgotten about them. Of the summation of k is equal to 1 to n. F of c sub k times delta x.
I never understood limits. But they never understood me.
So they never understood you.
Yeah. It's a hate-hate relationship.
Oh gosh, there's a lot of notes. Okay. Alright, so now I'm going to actually explain what an integral is.
Okay.
So you're going to need some space. I'm going to draw an integral and I'm going to write all around it. So you might want to leave a line or two above and below.
I like how it looks cool.
So, what color integral do I want? Pink. Good call.
White?
I wouldn't be able to see it.
I know.
Alright, there's a fancy integral symbol. You don't need to necessarily draw it that large, but I'm drawing it. Oh, that one didn't look nice. Hold on.
Remember.
Yeah.
Okay, it looks like a giant
Oh,
S.
look at. I'm so happy with myself.
It's from a to b, f of x, dx.
What does symbol represent?
It's an integral. I'm getting ready to label everything, so it'll make a little more sense. Let's see. Let's do like hot pink to label it. Alright, so simplest thing. This fancy S is just the integral sign.
Is it supposed to be a different color?
She just
I
said.
just said I'm using hot pink to label it.
Oh.
Are you upset, Josh?
No, they just look like the same color.
Oh, they do kind of look the same color.
Oh, I guess on the screen they do kind of look similar. Oh wait, that's volume, not that. Brightness, maybe. All right, the A here at the bottom is the lower limit of integration. Stop running away. B, as you might have guessed, is the upper limit of integration. Words kind of ran together. Now, f of x is just here in general, but this is representing a function, so this is the integrand, so it's what we're taking the integral of. And it's just any function is what f of x is representing. And then dx is the variable of integration. So we basically know what we're taking the integral of, because there could be different variables, like the problems we had in, I'm going to go back to related rates just for an example, right? We sometimes had like 3 different variables that we were taking the derivative of or whatever. But in this case, they would be telling us like we wanted a radius or something like that. And so that's kind of what that's saying with that part. Now, I'm not saying we're doing related rate problems with these. I'm just using that as a, it's kind of a visual for you. All right, now this entire thing is a definite integral evaluated from A to B. All right, we got another definition. So this is for area under a curve as a definite integral. It says if y is equal to f of x is non-negative and integrable over a closed interval A to B, then the area under the curve y equals f of x from A to B is the integral of f from A to B.
Instead of non-negative, I said if y equals f of x is nonsense.
I mean, you might feel that way sometimes.
That's funny stuff.
Then area is equal to the integral from A to B. Okay, when we are talking about an integral, we always say from the bottom value to the top value. So from A to B of f of x dx. Or we might also have the negative integral, whoa, that was not a good integral, from A to B of f of x dx for f of x less than or equal to 0. So basically, if the function is negative, we can take the negative out front, which is going to be a property you're going to find out about later, but that's essentially what that's saying. And so, in total, the integral from A to B of f of x dx is equal to the area above the x-axis minus the area below the x-axis. Okay, I wrote it really tiny, but it says below the x-axis because I don't want to go to another line. All right, and then we're going to have one more theorem here for this section. The integral of a constant. If f of x is equal to c, where c is a constant. Now remember, a constant can be 3, -5, pi, all those things. Okay, it's a constant number on the interval A to B. Then the integral from A to B of f of x dx is equal to the integral from A to B of c dx, which is equal to c times b minus a. Now you're probably like, what in the world? Okay, so an integral basically is telling you take the antiderivative. Okay, the difference with these problems, though, is that with a definite integral, we don't have the plus c part.
Okay.
Okay, with indefinite, we're going to still have that plus c because we don't know what it is. But this is giving us an interval that we're on. And so essentially, the reason this is the case is because c is a constant number. So this would be the integral from a to b of 5. Okay, the antiderivative of 5 is what? 5x, right? So then we replace x with b minus a because there's only one x in there. Okay. Otherwise, normally it's done in pieces, but because this is a constant, this one gets done all as one piece. But it'll make more sense when you actually see it with numbers and not letters in it. So that's all the notes. We'll do examples tomorrow and probably get through all the examples tomorrow.
No. I said yes because it perfectly went on the end of
Oh.
my second page.
That's awesome.
Sorry.
Oh,
It just made me happy.
I don't care. The way this has been, you deserve an easy one.